Hello, good afternoon, everyone. We are going to be starting lecture 2 today, which is on the topic of macromolecules. Before we actually talk about the biology aspect of the macromolecules, we have to first do a little bit of chemistry first. I just need to make sure that we all have the basic chemistry knowledge that is needed to understand some of the bio stuff in this lecture. So some of the things I'm going to go through with you might be a little bit of a repeat of what you've learned in chem class. So yeah, sorry, you had a question, Annabelle? No, okay. So let's start with a bit of chemistry here. First, let's start with matter. Matter is anything that takes up space and has mass. It takes up space, meaning it has a volume, and it has mass. That means you can weight it, and you're gonna be able to measure it in kilograms, grams, or something lighter, depending on what kind of matter you are looking at. And it can exist in different states. It could be a solid, it could be a liquid, or a gas. If you think about water, the water we drink is in the liquid state. You can freeze it to become a solid, or you can boil it to become a gas. Now, all matter is composed of elements. Elements, by definition, are substances that cannot be broken down into other substances. So if you think of carbon, for example, which is an element, the carbon atoms cannot be broken down into new substances. And carbon atom is the smallest you can go. On the other hand, if you think about water, water is H2O. You can separate water back into hydrogen and oxygen. So for that reason, water is not an element. And you can run electric current through water and it will split into hydrogen and oxygen. And so it can be broken down into other substances. That's why it's not an element. Now, what makes up an element? I kind of mentioned the word atoms already. Atom is the smallest unit of an element that still retains the chemical and physical property of the element. So if we're talking about the element carbon, all the carbon atoms will have the same properties as each other. Right? They have the same melting point, same boiling point. They are going to react in the same predictable way as any other carbon atoms. So that's basically what it is. It's the smallest unit of an element. Now, an atom contains 3 different types of subatomic particles. I think you probably learned about this in chemistry already. There are protons, which are positively charged. There are electrons that are negatively charged. And then we also have these neutrons, which are no charge. So protons and neutrons are in the center of the atom. We call that center the nucleus. Right? So over here, this thing here, the core, that's called the nucleus. And we have the electrons kind of going around in orbit around the nucleus. Okay, so elements cannot be broken down further, but element itself is made up of atoms. Different elements are going to have their own kind of atoms, right? Carbon is going to have carbon atoms. Oxygen is going to have oxygen atoms, right? Those 2 atoms are very different, but all the carbon atoms, they will share the same chemical and physical properties. So how do you know if something is an element or not? Well, we can look at the periodic table. The periodic table lists all the elements that has been discovered so far. Right? So if you want to know whether carbon is an element or not, well, you just have to look for carbon here. So there is carbon. Right? Now this is Not a very detailed periodic table. It doesn't have the names of the elements, but the one you have in chem class, they would have it, right? So oxygen is an element. Sulfur is an element. Iodine is an element, right? Something like water is not an element because you can't find it on the periodic table. It's not one single thing. It's a combination of hydrogen and oxygen, right? So that makes it a compound rather than an element. Okay, we're going to get more, we're going to talk more about compounds later on. So there are hundreds of elements that has been discovered so far. Some of these are actually man-made, right? They can synthetically create new ones by colliding them at really high speed. But even though there are hundreds of elements that exist in the universe, there are only 5 that makes up over 96% of the human body. And these include things like carbon, nitrogen, oxygen, hydrogen, and phosphorus. Okay, so carbon. Does anybody know where we can find carbon in our everyday lives? Give me some examples of where you might be able to find carbon. Okay, not quite what I'm looking for. Like pure carbon, I'm talking about. Okay, so like charcoal, right? Yeah, pencil, diamond, exactly. So charcoal, that's carbon. Diamond is pure carbon. And the pencil, right? Like this thing that you write with, people call it lead, but it's actually not lead. Lead is poisonous, right? So at one point it might have been lead, but now it's definitely not lead. That stuff is called graphite, which is carbon. Okay, so we have quite a bit of carbon in our body, 18%. We also have nitrogen. The nitrogen is in the air that we breathe. 70% of the air is nitrogen. 21% of the air is oxygen. And there is a little bit of hydrogen and phosphorus as well. The remaining 4% of our body are made up of these trace elements. Trace elements are elements that are only needed in small quantity. You don't need a lot of them, right? You just need a little bit of them for you to function properly. In fact, if you have too much of it, it usually will cause quite a bit of problems for you. So there are some examples of trace elements here. We have zinc, which is needed for your immune system. Many people are familiar with calcium, which is needed to have strong bones, but you also actually need calcium for muscle contraction as well. Too much calcium is not good. It will start to deposit in your kidneys, and it might contribute to kidney stones. Too much calcium in the blood can also cause uncontrolled muscle contractions. You might have a little bit of like uncontrolled twitching. There's iodine, which we need in the body to make hormones to regulate our metabolism. Does anybody know which organ in the body uses iodine? There's only one organ in the body that uses iodine. Does anyone know what it is called? What it is called? Thyroid, that's right. And for those of you who don't know where your thyroid is, it's right here. Okay, it's around the neck area. It uses iodine to make hormones to regulate your metabolism. And magnesium is another example of trace elements. Okay, so you just need a little bit of it. Yeah, someone asked me, is iron a trace element? Definitely. That was actually my next question. Like, do you guys know any other trace elements, right? So iron is another example. Maybe one more example. Does anybody know another example of trace element, something that you might be taking yourself or you've heard of it? What do you think? Melatonin is not quite an element. Okay, melatonin is hormone, so it actually is made up of a lot of different types. Fluorine, you mean like fluoride? Yeah, okay, that could be. Vitamin is not a single element, right? Like back to my point, right? Like there is nothing on the periodic table that says like vitamin, right? Like that's not it, right? Like there's nothing on the periodic table that says melatonin, right? So these are not elements. Okay, what we're talking about here are individual elements that we need. Okay, potassium. You guys have heard of potassium? Yeah, there you go. Sarah said potassium. Afra said sodium, right? Yeah, so lots of examples of trace elements. Okay. Deficiency in trace elements are going to lead to some health problems. Right? An example of that would be iodine deficiency. Iodine deficiency can lead to an enlargement of the thyroid gland, and we call that goiter. Goiter. There are different causes of goiter, though. Okay, like iodine deficiency is not the only cause. However, iodine deficiency is not a concern that we need to worry about in North America. Why is that? Where do you get your iodine in everyday lives? Do you know? I mean, certainly you
In the
can.
salt?
In the salt, that's right. Yeah, so you can take it as supplement. You can buy it. This one particularly is extracted from kelp, but normally speaking, our salt has iodine in it. Okay? They have been iodinized. They have been iodine has been added to the salt to prevent iodine deficiency. Okay? Natural sources of iodine include seafood, right? Shellfish. They are particularly rich in iodine. Calcium deficiency can lead to weakened bones, which we call osteoporosis. The bones can be very brittle, very what's another word for brittle? Like very easy to break. Okay, if it doesn't have enough calcium. So if a person has osteoporosis fall, they might have a fracture hip or something like that. So it's important to keep up with our intake of trace element. And I wouldn't recommend taking these supplements yourself. Like you should only be taking them if your doctor recommends you to do it. Right? Otherwise, you might overdose. Right? Like I said, too much calcium is actually not a good thing. It could cause it could contribute, increase your risk of getting kidney stones. All right. Next, we're going to talk about isotopes. Okay. Now, I told you earlier that the atoms of the same element, they have the same physical and chemical property, right? However, if you take a look at the carbon atoms has 6 protons. All right. So protons do not change. If you change the number of protons in an atom, it becomes a different atom. Right? You will learn that in chemistry class, right? You don't have to go back here. I'm just going to show you. Look, so this number on the periodic table, it tells you how many protons it has. Carbon has 6 protons. If you change it to 7 protons, then it becomes nitrogen. Okay, so all carbon atoms will have 6 protons. All nitrogen atoms would have 7 protons. All polonium atoms will have 84 protons. So protons of the same element do not change. However, the number of neutrons can be different. For example, carbon-12 has 6 protons and 6 neutrons. You don't have to worry about how to get these numbers, okay? I'm not going to ask you about them on the test. You'll learn it in chemistry anyways, okay? But I'm trying to make a point here. Carbon-13 will have 6 protons, but 7 neutrons. Carbon-14 will have 6 protons and 8 neutrons. So protons will always be the same, but the number of neutrons might be different. And that makes it a little bit heavier or a little bit lighter, depending on which type of carbon atoms you're looking at. So these variations that have same number of protons but different number of neutrons, these variations we call isotopes. Isotopes. Right? So isotopes are useful in different contexts. We can we can use isotopes because some of these isotopes are unstable, and when they're unstable, they can break down. Right? As they break down, they give off a little bit of radiation, which can be detected. So we can detect the radiation given off by carbon-14 to help determine the age of like a fossil. We can see how much carbon-14 is left in the bones of a person, or in a like a dinosaur or something, and we can calculate how old the organism was when it died. Iodine 131, that's radioactive iodine that can break down and give off radiation. So when a person takes iodine 131, it goes to the thyroid, and the thyroid gland will be exposed to the radiation from the breakdown of the isotope. And the radiation is supposed to kill the thyroid cancer, for example, thyroid tumor. If you have a smoke detector, there's a little bit of radioactive isotope in it as well. It's the americium 241. I mean, it's not harmful for us. It's not, strong radiation. It's all confined within the smoke detector, but it's something that's needed for it to work. Okay, so isotopes, same number of protons, different number of neutrons. Protons cannot change, neutrons can change, and electrons can also change. So sometimes it's possible for an atom to gain electron. Okay? It can gain even more than one, so gain electron or electrons. When they gain electrons, they become negatively charged. Right? Because electrons carry negative charge. So the more electron you have, the more negative it becomes. Right? It can lose electron or electrons, and then the atom will become positive. Normally, though, an atom would have the same number of protons and electrons, and it would be neutral. But it's possible for it to gain or lose electrons to become negatively charged or positively charged. Let's say sodium. Okay, symbol for sodium is Na. Sodium can lose electron to become Na positive. Chlorine can gain electron to become chlorine negative. Calcium can lose 2 electrons to become 2+. So all these atoms that have gain or lose electrons, we call them ions. And ions are important in our body because they dissolve in our blood, and it makes up what we call electrolytes. Right? Having the right electrolyte balance is essential for normal bodily functions. Like too high or too low of certain electrolytes is gonna more often than not result in some kind of problem. If you have too much sodium in the bloodstream, that's gonna end up causing your blood pressure to go up. So we don't want that. Okay, too much potassium in your bloodstream is gonna cause your heart to beat irregularly. We don't want that. Okay? But we need to have adequate amount of electrolyte in the body, and that's what like sport drinks are. Okay? When people drink sport drinks, it's mostly water and sugar, but there are important electrolytes as well, because when we sweat, we are sweating out electrolytes. Does everybody understand the difference between isotope and ions? Any questions? How, I see a question here. How does electron gain or lose? You're gonna learn that in chemistry, okay? But it's more simple than you think, okay? They literally just give it away. It falls off, okay? And when the electron is floating around, something else can capture it. That's the short answer. Okay, we had been talking about elements. These are things that cannot be broken down further, and they are made up of atoms. But atoms can come together in fixed proportions to form molecules. We already know water is an example of a molecule. It's 2 hydrogen combined with 1 oxygen. It's a fixed proportion. all the water in the entire world is H2O. Someone tries to sell you H3O, don't buy it. It's not water. Okay? In fact, if you change the ratio, you often end up with something different. Does anybody know what H2O2 is? Like, what if I have an extra oxygen? What is that? H2O2.
Is it hydrogen peroxide?
It is hydrogen peroxide. Very good. Okay, so hydrogen peroxide is like a disinfectant, right? Something you can buy from the pharmacy. Yeah, so these two have very different properties. If you drink hydrogen peroxide, you're gonna get poisoned, right? So just by changing one atom, it creates something completely different. So let's take a closer look at how this works, okay? Now we have the first picture here, we have sodium element. Sodium is actually a metal, right? And here is like a block of it. When we think of metal, we tend to think of something that's like, shiny, hard, strong. That's not really the case for all metal, right? Sodium is actually quite soft. You can cut the sodium with just a butter knife. That's what the person is doing here. It's cutting it, okay? And he's wearing gloves because sodium is very reactive in the presence of water and moisture. Now you can search this up on YouTube. There are people online who drop sodium into buckets of water and then you see spark flying all over the place. It's very, very reactive, okay? And that's why you have to wear gloves. And people actually have to store sodium under oil to prevent it from reacting violently, okay? So that's the sodium element. And if you were to zoom in, you will be able to see the individual sodium atom, right? So that's a sodium atom, so on and so forth. Because atom makes up element, right? Now I want to pause here for a second and just want to clarify something. Sometimes people think more about this and then they start to realize, there's some contradiction here, right? I'm telling you sodium is very explosive and it reacts violently with water, right? But then a moment ago, I was telling you that we need sodium in our bloodstream because it's an important electrolyte. So how come they're not like exploding in the body or whatever, right? Well, you got to understand when the sodium is existing inside our body, it's not the element sodium by itself, it's the ionized form, okay, of sodium. This is the one that has lost an electron, right, making it able to dissolve in our bloodstream, right? So even though they're both sodium, but it's not really the same thing, right? This picture I'm showing you, this is like solid sodium. This here is sodium that has lost electrons, and now they're more stable and they could dissolve in the water. Okay. Same thing for a lot of the things that you hear. Like you need to take your calcium pill. So the calcium pill, the white tablet that you're putting in your mouth, that's not pure calcium. That's not elemental calcium. It's calcium in a compound form. Okay. It's calcium that has been bonded with something else. So I just want to clarify that for you in case like it didn't make sense. Okay, so that's sodium. Now chlorine is another one. Chlorine is right here. It's this greenish, yellowish gas. And actually chlorine is poisonous, okay? It was used to make mustard gas in the Second World War. And it's very, very deadly. You breathe it in, it will destroy your respiratory mucosal, like the respiratory surface, and you basically die from it very quickly. If you were to zoom into the chlorine, you will be able to see the chlorine atoms. Okay? When you put sodium and chlorine together, they would react and it actually forms sodium chloride. Okay? Sodium chloride is table salt. Right? As you know, table salt are very stable. It's not poisonous, it's not explosive. We add it to our fries, make it taste better. So the compound that you get is very different compared to the elements that are used to create it. Okay? The properties of sodium chloride is completely different than the properties of sodium and chlorine. If you zoom in, to look at the sodium chloride, again, this is just like figuratively speaking, right? You're not actually going to be able to see these things, right? But if you were to see what really makes up the sodium chloride, then you would see these sodium chloride molecules, right? Each molecule is 1 part sodium and 1 part chlorine. All right, so each compound has a predetermined fixed proportion. Water is always 2 hydrogen, 1 oxygen. Hydrogen peroxide is always 2 hydrogen, 2 oxygen. Table salt is always 1 sodium and 1 chlorine. So how do they put the atoms together? Like how are the atoms being held together in a compound? Well, there is what's called a chemical bond. Right? Chemical bond. A bond it's like glue that holds atoms together. Glue that holds atoms together in a compound. And there are different types of glue. There are different types of bonds. We have the stronger ionic bond and the relatively weaker covalent bond. In ionic bond, there is a transfer of electron, okay? Sometimes more than one, and they tend to be stronger. Right? So for reason you will learn in chemistry, I know I keep on saying that, but you actually will, okay? For reasons you will learn in chemistry, sodium actually does not like having an extra electron, right? So it likes to give it away. It wants to give it away whenever it has the chance to do that. Chlorine, on the other hand, it really wants to have an extra one. So when sodium meets chlorine, it's the perfect combination, okay? Because sodium will give it out, will give away the electron, and chlorine would gladly take it, and then they partner out. Okay? It's like my 2 kids. Whenever they eat chicken, my older one does not like the skin, but the younger one really like the skin. Okay, so the older one always peel it off and then give it to the younger one. Right? It's perfect partnership. That's kind of like this here, right? The electron is like the chicken skin in the story. The other kind of glue is covalent bond. Okay, covalent bond. Instead of transfer of electron, there is a sharing of electron. Sharing of electron. Okay, sometimes can be more than one, and it's relatively weaker. It's still quite strong. It has to hold the atoms together, but it's weaker than ionic bond. It's weaker than ionic bond. All the molecules we will be looking at in this lecture, all the macromolecules that we'll be looking at, they are going to be held together by covalent bond. Okay. Let's talk about organic molecules next. Organic molecules are molecules that contains carbon. And this is a very different definition than when you say organic food, okay? That's totally not related. So when it comes to a molecule, the only thing to determine whether it's organic or not is to see if it contains carbon atoms. Many biologically important molecules are organic, such as glucose. Okay? Glucose is C6H12O6. Eventually, you will have to memorize this because we'll be talking a lot about glucose. But it's 6 carbon, 12 hydrogen, and 6 oxygen. Right? Protein is organic. It has carbon in it. Not all organic molecules are necessarily found in a living organism. Okay? There are many organic molecules in our surrounding that we use every day. Like polyester is found in your windbreaker, in your jacket, right? Polyethylene is found in a lot of plastics. Methane is an organic molecule. Methane is CH4. It's a greenhouse gas, right? That's given off from emission and pollution and whatnot. Now, there are some exceptions to this rule. What's CO2? Do you guys know CO2?
Carbon dioxide?
Carbon dioxide, that's right. So we're breathing out carbon dioxide, right? What about CO? Anybody know CO?
Carbon monoxide?
That's right. And you don't want carbon monoxide. It's poisonous. Carbon monoxide. And this one is cyanide. Okay, so these are the only exceptions, okay? People who made up the rules, they're like, you know what? Carbon monoxide, carbon dioxide, and cyanide, even though they have carbon atoms in it, we're not gonna call them organic, right? So that's all. Questions before I move on?
Why they don't call it?
Yeah, that's a great question. Okay, why not, right? I don't know. I didn't make up the rules, but the rough definition is because they, for the most part, is not widely found in the living system. Okay, it's not something that that can be incorporated into a living system. I think that was the definition that it was based on. But then, you know, the same argument can go for some of these things, right? Polyester and methane. But like I said, I don't know. It's just a rule. Okay, that was a lot of talking. Let's take some notes today. It's not a lot of notes. Okay, last class we wrote a lot of notes, right? Today we're just gonna write a little bit. Okay, and we're gonna start by talking about water. Water is H2O. So we're gonna draw some water molecules. Okay. And the way people draw water molecule is like drawing Mickey Mouse. There is the face, and then there are the ears. Okay, so that's a water molecule right there. This is the oxygen, and then the ears are the hydrogen. Okay, so in a water molecule, the H and O atoms are connected together. Connected by, do you remember what you saw a couple slides ago for water? Is it ionic bond or is it covalent bond?
Covalent.
Very good. Hydrogen and oxygen atoms are connected by covalent bond. Okay. That means they are sharing electrons. Sharing electrons. Now, sharing is an interesting concept. When I share something with someone, you know, the concept is like you are assuming you're sharing it equal amount of times, right? Like you get to use it half of the time and I get to use it half of the time. But sometimes it's not like that, right? Some sharing is not 50-50, right? Sometimes in certain situations, one person might be using it more often than the other, even though they're sharing, right? It's like toys for my kids. The older one is always hogging it and, you know, playing it more, even though they're supposed to be sharing it. And that's kind of the situation here with oxygen and hydrogen, okay? There is an uneven sharing of electrons between the oxygen and the hydrogen. And for reason I'm not gonna go into, because once again, you will learn it in chemistry later. For reason I'm not gonna go into, the oxygen is going to be pulling the electron towards itself more times, more often than hydrogen is able to do so. And by pulling the electron towards the oxygen, it makes it slightly, what do you think? Slightly positive or slightly negative if you pull the electron towards the oxygen?
Negative.
Slightly negative, yes. Now there is a fancy symbol for this. It looks like an 8, but you never finish it. So this is slightly negative. And for the hydrogen, it's going to be slightly positive. Now it's important to understand overall, the water molecule is still neutral. It didn't gain or lose any electron. It's just that the distribution of the electron is not even. They tend to hang around. They, as in the electrons, tend to hang around more around oxygen, so it makes it slightly more negative. Now that has that has an impact on how water molecules interact with each other. So if you have a few water molecules next to each other, like that, I'm just going to draw one more. Okay. Positives are attracted to negatives, right? Opposite attracts. And in this case, the slightly negative oxygen will be attracted to the slightly positive hydrogen. Okay. So these attractions between water molecules, we call them hydrogen bonds. Hydrogen bonds allow water molecules to be attracted to each other. Okay, so it's like a film that allows them to like cling on to each other. Think of them as tiny magnets that are attracted to each other. And this attraction, this hydrogen bond, is not just something that's unique to water molecule. Whereas we go through the lecture, you will see hydrogen bonds are very important in different kinds of macromolecules. Okay, but let's go back to water for now. Okay? These hydrogen bonds allow water molecules to cling on to each other, and that's the reason why we can suck water up a straw. When you drink from a straw, you are pulling on the water molecule, and the water molecules are pulling on each other, and it forms like a whole rope. Okay, and that allows them to travel up the straw. Let me give you another example. Right, this one is a little bit hard to visualize. Usually, I would demonstrate this in class, but in a virtual environment, it's a little bit limited. This is like a dime, all right? And this is an eyedropper, okay, like a standard one. And you know, we're gonna drop water onto it, like a standard size drop of water. How many drops do you think you can fit onto the dime? Just like, you know, spitballing here. And give me your estimation, okay, whatever comes to your mind. Okay, 10 drops. Okay, I hear 10 drops. Anyone else? 50 drops. Very steady hand there. Anyone else? Anybody think it's more or less? No, no more. Okay. Well, these are actually good answers. Okay? If you do it slowly, I think you can fit anywhere between 15 to 20 drops onto a dime. Okay. Now, if you do it correctly, then the water is gonna look something like this. It's gonna form like a dome, right? Can you visualize that, guys? So what's happening here is that the water molecules are actually grabbing onto each other to prevent them from spilling over, right? That is the hydrogen bond that's doing it. Okay? In fact, we have a special name for this kind of phenomena. It's creating surface tension to keep the water from spilling over. All right. Another way to visualize this is, you know, if you imagine like a table or something, and then I ask 20 people to stand on it. Right, so you will be able to fit like a few people on it. But if you want to put more people on, then you have to hang on to them, right? So that they're not gonna like fall over, right? So when you grab onto the other person to try to prevent them from falling over, that's kind of like what the hydrogen bonds are doing. The water molecules are grabbing onto each other so it doesn't spill over. Okay? So that's important because creating surface tension is related to a lot of the phenomena we observe in daily lives, okay? Including bugs being able to walk on water. It's because of the surface tension. All right, enough of that. Here, this shows you all the hydrogen bonds, right? Hydrogen bonds, hydrogen bonds, hydrogen bonds. Hydrogen bonds are between molecules, not within them, okay? Within a molecule is either ionic or covalent, but between the molecules, it's hydrogen bonds, okay? There are other ones as well, but that's the only one you have to know. Water is a interesting thing. We cannot live without water, and it acts as a very good solvent. Okay? A solvent is usually it's a liquid that would be dissolving something else. So if you think of one of these Kool-Aid packets, like little powders, cherry flavor here, you add it to the water and it will dissolve. So in this example, this would be the solute, which is what you are dissolving. And then you would have the solvent, which is what you are dissolving in. And then in the end, you get a solution. Now, I want to hear some examples of things that you can dissolve in water. Nothing fancy, just everyday life things that you might have in your kitchen, okay? What are some of the things that can be dissolved in water? Okay, we have powder milk, we have sugar, good, what else? Powder milk, I'm just gonna put like formula, okay, baby formula maybe. Salt, very good. Okay, so all these things are able to dissolve in water, and we call them hydrophilic molecules. Hydrophilic molecules. Hydro means water, and philic means loving. So these are water-loving molecules. They have no problem dissolving in them. So water can dissolve other polar or ionic substances. Okay? Most of the time. Remember, right? One of the first things I taught you is that even though we try to have these rules or in categories, but there are sometimes exceptions, right? So most ionic compound can be dissolved in water. Okay? There is a phrase in chemistry, like dissolves like. If they are both polar, then they would go well with each other. So anything that can be dissolved in water, we say hydrophilic. Hydrophilic. Can I have one more example, like maybe a liquid that mixes well with water? Again, something from the kitchen, nothing fancy, please.
Sugar and water.
Yeah, but I'm looking for a liquid though. Liquid, yeah. Yeah, sure. Milk can mix well with water. Maybe one more. Let's see if anybody can think of a. Yes, thank you. Yeah, Sophia. Yeah, that's what I was looking for, right? And Sarah as well. That the vinegar. Yeah, vinegar is hydrophilic because you're able to mix it well with water. It's gonna be able to dissolve within each other. What about something that cannot mix well with water? Something that cannot dissolve in water, right? Almost every time people are gonna say oil, right? And that would be correct. Oil is a hydrophobic molecule. Okay, a molecule is hydrophobic if it cannot be dissolved in water. Phobic is afraid of, right? Like people have different phobias, right? Like if you are claustrophobic, you are afraid of enclosed space, right? So hydrophobic means afraid of water. Things that are non-polar are usually hydrophobic. Okay, it's just not gonna mix well with water. So let me just recap for you the difference between polar and non-polar. Polar and non-polar are both neutral. They didn't gain or lose electron. The difference lies in the fact that those electrons in the molecules are distributed evenly or unevenly. If it's distributed unevenly, if they hang around one part more than the others, then it makes it a polar molecule, like water. If it's distributed evenly, if it's divided equally in all the places, then it's not going to have a slightly positive or negative end, and that makes it non-polar. Maybe one more example for non-polar things other than oil. What is something else that cannot mix well with oil? With water.
Gasoline.
Yeah, exactly, right? Gasoline, right? You see that in pictures of like oil spill, right? Like in the ocean, there's that, kind of like a film on top of it, right? That's usually a little bit like bluish yellow and sometimes pinkish hue, right? That's gasoline. That's non-polar. Very good. I wasn't thinking about that, but that's a good example. Wax is another example, right? And you drop hot wax in the water, it cools, and then it flows on top. All these things are non-polar, okay? They are hydrophobic.
What about blood?
Blood? That's a great question. Uh, what do you think? Have you seen blood in water? Like, does it go mix well in it?
I don't know.
No, yeah, it does. It does. Okay, like blood is able to dissolve in water. Yes. Okay. We'll learn more about blood next semester. We should actually have a whole lecture on blood next semester, which is very exciting. Okay. I have a private message asking, does nonpolar usually flow or sink? It depends. Okay, some nonpolar stuff are more like whether something flows or not has nothing to do with it, whether it's polar or non-polar. Whether it flows or sink has to do with its density. So things that are more dense will sink to the bottom. Okay, so in this case, oil and gasoline, they are less dense than water, so they float to the top. Okay, you can have things that are heavier, that are like denser, and they would sink to the bottom. Yes, pH scale. So pH scale is a measurement of whether something is acidic or basic. Right? The scale goes from usually it goes from like 0 to 14. Theoretically, it can go higher or lower, but between 0 and 14, if the pH is less than 7, then it is going to be acidic. Okay, things that are acidic include like citrusy stuff, right? Like lemon juice, tomato, lime, orange, all that kind of stuff. And we also have a bit of acid in our stomach to help digest our food. So all these stuff are acidic. Okay, vinegar is acidic. Whereas if the pH is greater than 7, then is basic. Okay, basic. Baking soda is basic. It's usually bitter, these kind of things. If you touch it, it's a little bit slimy, like bleach, right? Soap, they are all basic, and it's greater than 7. If it's 7 exactly, then it's neutral. Right? Pure water is neutral. Okay? It has to be pure water. Tap water is not necessarily 7. If you leave water out in the open, it actually will not stay at 7. It will suck up the carbon dioxide in the atmosphere, and it will become a little bit more acidic. But less than 7 is acidic, higher than 7 is basic. 7 is neutral. Blood, as we were talking about earlier, actually has a very narrow pH that is compatible with life. Okay? It's between 7.35 to 7.45. Anything outside of these ranges is going to cause quite a bit of problem and potentially lethal. So if the blood is too acidic, then we call it acidosis. If it's too basic, then we call it alkalosis. Okay, don't worry too much about it. I'm not going to test you on it. I'm just showing you these things. All right, and we have different mechanisms, different ways to help maintain this homeostasis in our body. Our respiratory system, urinary system can both work to help maintain the pH of the blood for us so that we don't, go outside of the survivable range. There are also these things in your blood called buffers that will help prevent drastic changes in pH. So we'll learn more about that later on. Okay, very quickly, let's do a poll question, and then we'll see where this goes. Go ahead. All right, I do try to keep it under a minute, so if you can choose something, that would be great. I only have 5 answers. Kind of sad, but if you're able to choose something, please choose something. Okay, we'll stop for this one. Maybe you can try. Oh, the poll didn't show up for you? Oh, okay, maybe that's why. Is that true for many of you that didn't show up? Is that why there's a little participation? All right. Okay, if you don't see the poll, that's okay. You can still do the question on your own. So water is a polar molecule because the correct answer is C. Okay, because it has uneven distribution of electron, right? It's not sharing the electron evenly, and that makes it polar. Partly negative, partly positive. That's it for the chemistry. Finally, we can move on to biology. Right? So we're going to be looking at macromolecules. And you know, it can be a little bit overwhelming because there is a lot of information that I'm telling you. But the key is to, you know, review them with the study guides and ask questions. So there are 4 main types of macromolecules that are found in the body: carbohydrates, proteins, lipids, and nucleic acid. I think we only have time for carbohydrates today. You guys are my 3rd class, so I'm saying this for the 3rd time in the last 2 days, okay? And my other 2 classes, we are only able to go through the carbohydrates, right? So I think that's also what we're going to be able to do. Here, macromolecules, you can think of them as a polymer, okay? And a polymer is basically a long chain of repeating building blocks. Okay? With the exception of lipids, right? This is the exception. Carbohydrates, proteins, and nucleic acid, they are all polymers, long chains of building blocks. Now, depending on, do you have a question, Elvis? I see your mic.
No, it's
Okay. Yeah. So depending on what you're building, the building blocks are going to be different, right? The best way to visualize this is to think of a train. Okay? A train is very long. It's like a polymer, and it's made up of repeating carts. But depending on what kind of train you're looking at, the carts that you use to build a train would be different. Like the carts you have on a GO train would be different than the carts you have in a TTC subway, right? Which would be different on one of those like CN rail train, right? Okay, or if you're looking at like a bullet train or something, it's going to be very different, the blocks that you use. And that's what happens here. Even though these macromolecules are all polymers, the building blocks we use for them are going to be different. For carbohydrates, we use something called monosaccharides. For proteins, we use amino acid and so on and so forth, right? We will go into more detail about what these things are as we progress. So, you know, don't worry too much about it at this moment. These building blocks, these subunits, we have a name for them. We call them monomers. So let's put it together in a you know, summary figure for you, and hopefully it'll make more sense to you. Try to draw this a little bit bigger because we will be coming back to it to add more details to it. Okay, so let's say we have these little circles. Okay, so these would be the building blocks, okay? The subunits that will be used to build the macromolecules. So these are the monomers. Okay, remember different macromolecules would need different monomers. I might need the pink ones for carbohydrates. I might need blue ones for proteins, so to speak. Okay. And then what happens is we can connect them together. I can connect them together. Right? So just join these things together and you get a chain. This is not a particularly long chain, but it illustrates the point. This would be a polymer. polymer. Now, to connect them together, to connect the monomers together to form the polymers, there is a chemical reaction. There is a process to do this. The name of that process is called dehydration. Dehydration synthesis. Synthesis is to create. Dehydration is, what does dehydration? What do you lose when you're dehydrated?
Water.
Exactly. So this is create something by removing water. I'll show you more on that in a bit. Another way to describe this, another name for the same thing, is condensation reaction. Okay, when there are condensation, it's like water coming out from the air, right? So in this case, we will be removing water. Now, when we have polymers and we want to break it back down into monomers, we will have to add water. And the reaction here is called hydrolysis. Hydro means water. Lysis is to break. So I'm breaking the polymer with water. Okay, so when we eat food, when you eat your carbohydrates, when you eat your proteins, the food that goes into our body are in the form of polymer. And our digestive system is basically going to be adding water to it and performing hydrolysis so that we can break it back down into its individual building blocks. We can absorb these building blocks as nutrients. We can use them to build other molecules that we need in the body. Okay, so the polymer here is like the train. These are the individual parts that builds up the train. Any questions? Okay. Let's take a look at here. We have one molecule here. Never mind what the hexagon is for now, okay? It'll make sense in the end, I promise you. This is a monomer, one of those building blocks. This is another monomer. And we're trying to connect them together, put two and join them together using dehydration synthesis or condensation reaction. What that means is you will take the H, the hydrogen from one of them, and then you will take the OH from the other one. And afterwards, a water molecule will come out. The H and the OH becomes the water molecule that comes out. And then you can connect the two molecules together. So now the two monomers are joined, right? And what is this bond called? It's a type of covalent bond that connects them together. Okay. The opposite is true when I want to break it apart. Right, so like if we want to digest this molecule, we would add a water molecule to it, and then it will be able to break the bond, and it will go back to the monomers. So that process is called hydrolysis. Once again, hydro is water, lysis is to break. Just one quick poll question with you, and then we're gonna take a break. Let's say we have, let's take this example here. In this example, we have 1, 2, 3, 4, 5, 6, 7 building blocks, 7 monomers. If I want to join all of them together, how many water molecules needs to be removed? Okay, let me give you some choices so you can do it. Is it how many? 1, 2, 3, 4, 5, 6, 7. Okay, so is it 6? Is it 5, 6, 7, 8? Or you can say not sure. Okay. How many? If you see the poll, you can do it. If you don't see the poll, I don't know, maybe update the Zoom or something. Sometimes it doesn't show up on phones and stuff like that. But you can still participate. You can type your answer in the chat box if you want. Yeah, the question was like if I were to join all these building blocks together, how many water molecules will be removed? Okay, if you need to connect all of these together, how many water molecules needs to be removed? Okay, very good. I have more answer this time than before. The correct answer is 7. 7 water molecule. Okay, let's see how many bonds we need to form to connect them together. That's 1 bond, 2 bonds, 3, 4, 5, 6. Oh, sorry, it's not 7. The answer is 6. Okay. Every time you connect a bond, every time you make a bond, every time you connect them, you're gonna need to remove a water molecule. So we have 1, 2, 3, 4, 5, 6, 7. We have 7 of the monomers, and we only need to make 6 connections. So that's 1 water molecule coming out, that's another water molecule coming out, so on and so forth. So this will be removing 6 water molecule. Okay. By the same token, if you are going to break this polymer, you will have to add 6 water molecule as well.
Yeah, it's the number of monomer minus 1.
Exactly, yeah. If you have X number of monomers, then the number of water molecule you need to remove is X minus 1. All right, let's take a break, and we will definitely do more when we come back, okay? 5 minutes. See you guys soon. Okay, let's continue with this. All right. Now, I still haven't tell you what the hexagon and the pentagon represent. I will, okay, it will make sense in a bit. But, just take a look at this question here. We have a hexagon here with an OH, and we have a pentagon here with an OH. If we want to join them together with dehydration synthesis, what would be the outcome? What would be the product? Okay, anyone else? Last call. Again, if you don't see the poll, you can send me your answer by private message if you want, or so I can see it as well. All right, so let's see. The answer is kind of all over the place here, but we have again hexagon here and a pentagon here. So I need to look for answer that has one of these things, one of each of these things, right? So definitely not C. C are like 2 pentagons here, right? And definitely not D, because that's like hexagon and hexagon. So I need to have 1 hexagon and 1 pentagon, right? So it's either A or B. Now, here, when we connect them, we have to do dehydration synthesis, which means we have to remove a hydrogen from one and OH from the other. Doesn't really matter which one is which, okay? So if you remove the H and you remove the OH here, don't forget there is an oxygen left. So when you form the bond, right, you have to have the oxygen here. So the answer is B. Does anybody have any question about this question? Okay, I hope it makes sense to you. Some of these concept track questions will show up on quizzes and tests, okay? So make sure you revisit them when you are preparing for them. So we will now talk about carbohydrates specifically, starting with the chemistry of carbohydrates. Carbohydrates are organic molecules, and so are the other three: lipids, proteins, nucleic acid. They are also organic molecules, meaning they contain carbon atoms, right? That's all it means. There's nothing special about it. Do you remember the 5 elements that makes up over 96% of the body? Right, let's mentally recall them. It's carbon, hydrogen, oxygen, and then there are 2 more, right? Do you remember what it is without looking back?
Phosphorus.
Phosphorus, yeah, and Sophia said nitrogen, very good, right? So of the 5 here, carbohydrates are made up of CH and O. Okay, CH and O, they are like a very common triplet, right? You will see them in all 4 types of the macromolecules. Carbohydrate, the word carbo means carbon, and hydrate means water, as in H2O. So carbohydrate has this ratio of one carbon to every water molecule. If I say N is 6, and N can be any whole number, but let's say 6, then it will be C6H 2 times 6, which is 12, and O6. Does anybody remember what this molecule is called? I mean, I said it once today.
Sucrose.
Yeah, it's close, very close, okay? But Sarah, you got it right. It is the glucose. Glucose. Now, you guys might not recognize it just yet, but we will be talking about glucose so often that you will soon realize or recognize C6H12O6 is glucose. Now, we don't consume glucose in its in the glucose form. What I mean is, like, you cannot buy glucose. I mean, you can, but it's like very uncommon. Okay, like it's not like a bottle that says glucose and then we chuck it down or something like that. Okay, but the carbohydrates that we consume, they can be broken down into glucose, and you will see what I mean by that in a second. But first, let's talk about what the function of carbohydrates are. For us, for humans and many other life forms, carbohydrates are important for quick, short-term cellular energy. Right? As we speak right now, all the cells in your body, a lot of them are burning glucose to help create energy. You might be thinking, well, I'm not doing much. I'm just sitting here, listening to you talk. That doesn't really require much energy, right? Does it? Well, it actually does, right? Your heart is beating. That requires energy. Right? If you're copying notes, moving your muscle, that requires energy. Breathing requires energy. Even when you're sleeping, right? Your brain is not really shut down or anything, right? That also requires energy. So to provide sufficient energy for all these things that are happening day in and day out, you are burning glucose to create that energy. Some other organisms, like plants and some animals like clams or lobster, they have special kind of carbohydrates that help them form structural components. So plants, there are fibers in them, right? The fibers is a type of carbohydrates. The shells of shrimp and lobsters, that actually is a type of carbohydrates. Okay, but for us, for humans, we do not use carbohydrates as structures. We just use them as fuels. How do you burn the glucose for energy? I hear some of you say. Well, the process by which we burn glucose is called cellular respiration. It is the main chemical reaction in the body for producing energy. For producing energy. And it goes something like this. We have glucose, which again we get from our food source. We are not consuming it in the form of glucose, but the food we eat will be converted into glucose. It reacts with the oxygen that we breathe, and it converts it into carbon dioxide and water, and more importantly, energy. Now, this reaction is something we will spend a whole week talking about later in lecture 5. Okay, but it's it's not a unique reaction. Okay, as you will learn soon in chemistry, that there are many similar reactions that happens in other situations. For example, you don't have to write this down. Okay, you just have to listen. If I substitute glucose with octane, then you are burning octane to produce carbon dioxide, water, and energy to move your car. Okay? The gas that you put in your car is actually octane. And when you burn it, it creates energy to move it. Okay? What about barbecue? If you have a barbecue, what kind of gas do they put in the tank? Propane, that's right. So instead of using octane, you can use propane. And when you burn the propane, it produces carbon dioxide, water, and energy to cook your food, right? If you have a lighter, like a lighter, then it's butane, right? And it produce energy to light up something. So these are combustion reaction, we call them, because we're always burning things. And in the body, we are burning glucose like all the time, 24/7, right? The moment we stop burning glucose, then we don't make enough energy. Our heart cannot beat. We die. Okay. Does that mean we cannot burn other things? Like what about the proteins and the lipids that we consume? Can we burn those? Yeah, we could. But remember, this is the preferred source of energy for your cells. Okay, so where do you get your carbohydrates, right? If you think about the lunch that you had, what kind of carbohydrates may be in your lunch? Give me some ideas. If you had lunch, okay. If you didn't have lunch, maybe you had some breakfast. What did you eat today that contains carbohydrates? Just wanna, yeah, bread, exactly. Bread has quite a bit of carbs in it. Anyone else?
Rice.
Rice, yeah, okay. Bagel, potato, yeah, very starchy stuff, right? So they are all very rich in carbohydrates. These are very healthy choices, though, okay? I love them. So starch comes from all these places. Fructose, as the name implies, these are naturally occurring sugar in fruits, right? If you think of like a ripe banana, it's sweet, it's because of the fructose, okay? Watermelon is sweet, it's because of the fructose. Sometimes you can have fructose in corn syrup. And if you look at a lot of like a processed food, they have what's called high fructose corn syrup, yeah? And people are trying to, cut down on those because it's highly processed and it's not healthy, yeah? Lactose, you will find it in dairy products. And the unhealthy kind of carbohydrates you will find in candy bars. And the one you use in the kitchen, those are actually sucrose. Yeah. So when we say sugar, sugar is just like a broad term. Like there are many different kinds of sugar. On this page, I show you 3 kinds: fructose, lactose, sucrose. They are all actually sugar. Okay? But when we, in our daily communication, when we say sugar, we automatically think about like what's in the kitchen cabinet, right? Same thing with salt. When you say salt, you're thinking about the salt you have in your kitchen. You're not thinking about like raw salt, right? So both of them are actually salt, but they're a different kind of salt. So I want you to remember this, okay? Sugar is a type of carbohydrates. And even within sugar, there are different kinds of sugar. Now, let's talk about how we make carbohydrates. Okay, so carbohydrates, as I have been telling you the whole day, is a macromolecule. Because it's a macromolecule, it's a type of polymer. It's very, very long, like those trains I've been telling you, and it's made up of individual building blocks. So the building blocks that we use to make the carbohydrate polymer are glucose, fructose, and galactose. Okay? There are more kinds of monomers that can be used, but these are the three that I want you to remember. Okay? They are single sugar that are kind of on their own. So we have a name for them. Okay? Monosaccharide. Monosaccharide. Mono means single. Like if someone speaks in a monotone, right, then it's just a single tone. There's no variation in the voice. Like a monorail only has one track, right? So monosaccharide is single sugar. Okay, saccharide is sugar. And when you look at the chemical structure of these monosaccharides, they look like this. Glucose, for example, has a hexagon ring. Fructose has a pentagon ring. So that's what these things were. You don't have to go back. Okay? That's what these things are. Right? The hexagon represent the glucose ring. The pentagon represent the fructose ring. Right? It's like a simplification of what the actual structure is, right? No one's gonna ask you, like I'm not gonna ask you to identify these things. Okay? I think that's like unfair question. I'm not gonna give you a picture of this and say, hey, what is this? And you have to tell me it's glucose. Not gonna happen, okay? You don't have to recognize them, you don't have to draw them. You just have to remember that the monomers of carbohydrates are glucose, fructose, and galactose. Okay.
What is galactose?
Yeah, so like where would you find it, right? Okay. Again, it's very rare to find it by itself. It's usually connected with glucose, and I will show you what it looks like in just a bit. Okay, so hold that question. I promise you will have the
Thank you.
answer in a bit. All right, so these are single sugar, okay? Monosaccharide. They are single and they are ready to mingle. Let's say we have the glucose here and we have the fructose here. They are both single. They are both single sugar, monosaccharides. So let's pair up, let's partner up, right? And that's exactly what happens here. If you do dehydration, I know I repeat a lot, but that's my way of helping you remember some of these things, hopefully. If we do dehydration synthesis, where you remove a hydrogen and an OH, then you can connect them together. You can form a covalent bond. We learned this before the break, right? Then now the glucose and the fructose are bonded together. And what do you get? You get sucrose, right? Remind me, where do you find sucrose again? I mean, like if you look at a picture, you might say candy, but like, in your house, where are you going to find sucrose?
Sugar.
Sugar.
Yes, but like kitchen sugar, right? Kitchen sugar,
sugar.
right? Okay, yeah, to be specific. Okay, I know what you mean. Okay, yeah. So like if you open your kitchen cabinet, you see the white stuff, right, in the container. You're like, oh, yep, that stuff is actually sucrose. Okay, when you eat candy, the candy, amongst other things, are gonna have sucrose in it. So what is sucrose? Sucrose is just a combination of glucose and fructose connected together by a chemical bond. So when you eat candy, you are consuming sucrose. When it goes into your body will break the sucrose back into glucose and fructose. What are you going to do with the glucose and the fructose? Well, the glucose you are going to burn. You are going to use this reaction to burn it. That's why, like, sometimes you eat a candy bar like if you're sleepy in class or something, you eat a candy bar and you might feel a surge of energy. You might feel a surge of energy. That's because you are burning the glucose from the candy, right? And that provides you with energy, right? What about the fructose? What are you going to do with the fructose? Well, we're not going to talk too much about it, but fructose in the body can actually be converted into glucose, and then you can burn it again, okay? So that's basically what sucrose is. Sucrose is no longer a single sugar. It's a double sugar. It has two sugar molecules connected together, right? So for that reason, we call it a disaccharide. Okay? Monosaccharides can combine to form disaccharides. And there are different kinds of disaccharide that I want you to know. 3 kinds, okay? They all have glucose in it. They all have at least one glucose in it. So, glucose, glucose, glucose. The ingredients to make them are monosaccharide. And then the outcome, like these guys, they are disaccharide. Okay. So let's take a look at some of these things. I already told you on the previous slide, glucose plus fructose is going to give you the sucrose, kitchen sugar, okay? Kitchen sugar. Glucose plus galactose is going to give you lactose. So someone asked, like, what exactly is galactose? Like, we're not going to be consuming galactose as is, but every time we eat like ice cream, cheese, yogurt, we are ingesting lactose. And when your body breaks down lactose, you get the glucose and the galactose. Okay, glucose you can burn, galactose you can actually burn as well. Okay, but remember, glucose is the preferred form of energy. What do we call people who cannot break down lactose? It's gonna make them ill if they eat dairy stuff. Lactose intolerant, that's right. Okay, so they lack the we call it the enzyme. More on that later. They lack the enzyme to break it down, and so they get sick. Okay. Glucose plus glucose gives you maltose. Maltose. Anybody know where you will find maltose in food?
I don't know. In a drink?
Yes. What kind of drink? Maltose. Malt. Yeah. Malt. What is malt? It's like an alcohol drink, right? So like in beer, there's quite a bit of maltose. That's why, beer has high calories. Actually, people who drinks too much, they tend to gain weight from it. Okay, so these are all disaccharides. Okay, and these are all monosaccharides. You can expect questions where I ask you to, choose all the monosaccharides from the list. Okay, or I can ask you, glucose plus galactose. What does that give you? You have to know it's lactose. Okay, so lactose intolerant. Right? In order to break these things down, in order to break down maltose, you would need to have the enzyme called maltase. In order to break down lactose, you would need to have the enzyme called lactase. In order to break down sucrose, you would need to have, I think you see the trend now, right? Sucrase, right? So things that ends with ASE, it tells you it's an enzyme, right? Enzymes, we'll learn more when we get to the proteins, but they are basically protein that helps you do a reaction in the body. So people who are lactose intolerant, they cannot digest the lactose properly because they don't have the lactase enzyme in their body, right? People who are not lactose intolerant, they can make the lactase, right? And then they could digest the lactose. But without the lactose cannot be broken down, and instead the bacteria are feasting on it in your intestinal tract. And all these extra bacterial activity causes bloating, gas production, diarrhea, and it's very unpleasant. But fear not, if you are lactose intolerant, you can still enjoy a nice milkshake or chocolate sundae. you just have to pop one of these pills first. Okay, so it's like the actual enzyme, but instead of you making it, you are taking a pill for it. Okay. All right. We went from monosaccharide, single sugar, and we combined them to make disaccharide, double sugar. But as you recall, carbohydrates are long chains of repeating units. Okay? So we're not going to stop at 2. We can keep on adding more and more and more and more, and we get the polymer. The polymer that we make for carbohydrates, we call them polysaccharides. It shouldn't be surprising, right? We go monosaccharide, disaccharides, and then now we have polysaccharides. Some of them are straight, like this. If you look into it, they are like beads on a string. Okay, I'm not going to draw the whole thing. Some of them are branched, so it comes off like this. Okay. Some of them are extensively branched. Okay, for real, that's what they look like. Okay, but nevertheless, if you zoom in, you will see the glucose, glucose, glucose. Right, all these are glucose. It's just about how they're connected together. Right? Sometimes there are hundreds of glucose in the polysaccharides. Other times, thousands. Okay? There are different kinds of polysaccharides. The ones that I want you to know, well, there are 4 I want you to know, and there are 3 here. Cellulose, glycogen, and starch. These are all made up of glucose. Okay, so we're going to forget about the galactose and the fructose for a second. Just focus on the polymer that we can get with glucose alone. Okay? Each of these have very different chemical properties depending on how the glucose are linked together. Like I said, some of them are straight chains, some of them are branched. So let's start with cellulose. Okay? First of all, just so we are clear, you and I, we do not make cellulose. Okay, we don't have cellulose in the body that we make, and cellulose is just something that is naturally found in plants. Okay, it's found in the plant cell wall. We're gonna learn more about cell wall later, but you know what a cell is, right? You should by now. Cell is what makes up a living thing, right? I think last week we said all living things are made up of cells. So plant have cells, and protecting the cells, protecting the plant cells are an extra barrier. Okay, that extra barrier that protects it, it's called the cell wall, and that is what makes up the fibers of the plant. Okay, that's the cellulose that we are talking about. It's really strong stuff, very tough fibers, and cellulose are straight chain. So that's one chain of cellulose. These hexagons are glucose, right? Okay, that's another strand of cellulose. Cellulose. Okay, cellulose, and then another cellulose. All right. And what the plant does is they take these individual cellulose strand and they actually braid it together like a rope, and that make it really, really strong. Okay. Now, we don't make cellulose, I told you that already, but we can consume them, we can eat them, right? In fact, when we eat vegetables, when we eat high fiber grains like quinoa, brown rice, they have a lot of fibers in them, okay? We are not eating the fibers for energy because we don't have the enzyme to break down the fibers. We don't have the enzyme to break down the cellulose. But these dietary fibers, they help us move things along in the digestive tract, okay? And it's essential for good health, actually. So we should increase fiber intake in our diet, even though we're not eating it for energy, okay? It's still an essential part of a healthy diet. Animals that graze on grass, for example, they have special bacteria that lives in their gut that would help them break down the cellulose. Okay, Did you know cows have more than one stomach, maybe? Right? Maybe you know that, I mean. They do have more than one stomach. And if you ever look at a cow, they are always chewing. Right? They eat the grass and then they chew, 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 chew. They swallow it. And then the cellulose in the grass is so tough that they are not going to be able to break it down in one go. So then they kind of regurgitate it back up, and then they chew more, and then they goes back down for more digestion. So this happens a couple times until it's fully digested. Okay, and the special bacteria in the gut help them do that. Random facts on the side: every time the cow burps up the food to chew more, it actually burps up a lot of methane gas, CH4 as well. Okay, and cow farm is one of the leading cause of greenhouse gas emission. Okay, they contribute a lot to greenhouse gas emission, and that's why people say, consuming beef is actually really bad for the environment, and it's because of that reason. Okay, chicken is much easier, much better. Okay? They don't really produce these greenhouse gas. Okay, that's it for cellulose. Let's move on to starch. Starch is the storage form of energy in plants. Okay, if you think about all the starchy stuff that we eat, like the potato, the yam, the cassava, all that stuff is part of the root or the stem of a plant. Okay? The plant sits in the sun and they make food for themselves, and they store the extra food that they make in the roots and stems as starch so that they can use it during the winter. We, of course, harvest them and we eat them, and then we can break down the starch. Look at the starch here, right? What is the starch made up of? Right? These little hexagons, they are all glucose. Right? So that's why we're eating the starch. When we digest the starch, we are breaking off the little glucose, and then we are burning it for fuels, right? We're burning it for energy production. So you and I, we do not make starch. We just eat them. Right? We consume them. So where do we store our extra energy? What if you eat more than you need, right? Like where are you going to store them? Well, the storage form of energy for a lot of animals would be what's called glycogen. So if you look at the diagram for glycogen, it's very similar to starch in that, it's branched. There's non-branch version for starch as well. But for glycogen, it's very, very extensively branched, okay? So like you have the main branch, and then you have all these side branches, and then you have more branch from the side branches like that. Okay, so we store them, we store the glycogen in muscle as well as liver. And they function as like an energy reservoir. If you're fasting, if you skip a meal, then your liver is going to release the glucose from the glycogen so that you have fuel to go on. Okay. So this picture summarizes all the different kinds that we talked about. We have the starch in the potato that the guy here is holding, the muscle on the arm, that's where you can store some of the glycogen. And then we have some plant leaves here, which are mostly cellulose. The last type of polysaccharide I want you to know is something called chitin. Chitin. Right? Chitin is a polymer of special glucose. These are glucose that has been modified to include nitrogen. Okay, they're naturally occurring, okay, by the way. And you will find them in the hardened parts of small animals such as crabs, crab shell, lobster shell, shrimp shells, and the exoskeleton of insects, like we have an endoskeleton, right? Like our hard bony parts is on the inside, but for these organisms, their shell is on the outside, and the shell is made up of the chitin. Okay, so it provides structural support, very strong. For us, for humans, we found out we can actually produce strong, stretchable, flexible surgical threads using chitin. Okay? So it's good to use chitin as surgical threads because they are biodegradable. If you go have like your wisdom teeth removed or something, they could stitch you up with the chitin and it would just melt in your mouth. Right? So you don't have to go back to remove the stitch. It allows better wound healing, and if it's like something on the outside of the body, it doesn't leave as much of a scar. And that's the use of chitin. Okay, all the chitins are made like completely synthetically. Okay, it's not like they take it from the crabs or something like that. Okay, it's nothing like that. That's it for carbohydrates. Okay, let's do 2 poll questions, and then we will almost be done. Okay, yeah, everybody who chose something got it right. It's just something you have to memorize, right? And it's glucose and fructose. That gives you the sucrose, which once again is your kitchen sugar. Okay, this is an example of a multi-select question. I told you there will be some of these on the quiz and test where you have to choose all the right answer. So let's try this one. Select all the false statements. Okay, that was more than a minute now. I think I'm gonna take it up. So we're looking for the incorrect statements. We're looking for the false one. First one, polysaccharides are important for both energy storage and to provide structure to cell. Yeah, that's true. Energy storage is starch for plants and glycogen for animals. Structure support would be cellulose. Okay, so that's a correct statement. We're looking for the false one. Okay, so we're not going to choose A. Glycogen is important for both energy storage and to provide structure for cells. That is incorrect. It does not provide structure for cells. That would be cellulose. Cellulose is found, it's only found in animals. Not true. We don't have cellulose. Okay, we don't make them. It's found in plants. So that's a false statement. These are all examples of monosaccharides. It's correct. Starch is the storage polysaccharide made by plant cells. That's also correct. So only B and C are incorrect. Okay, so these questions will be worth 2 marks on the quiz and test, and it will tell you in the question to choose all the correct answers, right? And for the ones that only have 1 correct answer, it won't let you choose more than 1 anyways, right? So like there won't be any confusion. I think that's it for today, okay? Make sure you start working on the study guide. For example, let me just quickly show you here in the lecture 2 study guide, right? There are these questions that you can do to help you reinforce what you've learned, right? A chart to summarize all the polysaccharides that we've learned today. I'll post the answer to these as well for you to check, but please work on them yourself. We don't have any evaluation coming up, nothing for next week. Our first quiz is going to be on the 23rd though, okay? So mark that down if you haven't already. That's it. Thank you again. Have a good rest of your week. Take care,
I have a
guys.
question.
Sure, go ahead.
The first